Okay, so I welcome everybody to the first edition of this year's Applied Machine Learning Seminar in Diagnostic Imaging. While still are people joining, I think I quickly say something about the overall program before I start introducing our today's guest. So I think we created a quite interesting and really great program for this year with a lot of topics and a lot of talks from really experts in the field. The program this year is a little bit subdivided in either research and development topics or innovation topics. So in the research and development topics, we talk about, or there's talk about strategies for conducting a solid translational research. And in the innovation topics, there we want to create an environment, or people talk about the creation of an environment which relies on their complementary resources and expertise. So I think this year's program is a really great opportunity to dive deep into machine learning, how it is applied in the clinical routine from different perspectives. And I'm really happy and proud that we could create this great program. Of course, also my thanks goes out to Davide, Christina, and Katharina, and everyone who was involved there. So now I have the big pleasure to introduce our today's guest. Our today's guest is PD Dr. Daniel Truhn from the RWTH in Aachen. Daniel and I have a little bit of history. We used to work together at the RWTH in Aachen at the University Hospital when I was still working there before I left for Zurich. Daniel is still there, where he is now leading the machine learning group of the radiological department there. And he has a doctor in medicine. He studied medicine as well as physics. So he's quite a unicorn there. There are a couple of those people when you look at radiologists who studied physics and medicine. And I think he's brilliant in both of those topics. And Daniel is also the principal investigator of the ODELIA project, which was now funded from the European Union. A big funding was received there. And this is a multicentric project, which is investigating breast MRI for federated learning. So cancer detection, lesion detection for breast MRI using federated learning, and multiple institutions are involved there. One is, of course, Aachen, and then there is the University of Dresden, Barcelona, Athens, Cambridge, and also we from the University Hospital Radiological Department has the pleasure to work there together on this project with Daniel. So Daniel, I'm really happy that you made it this time and to hear your talk. And Daniel will talk about transforming healthcare with AI and how potential application and challenges could look like. So Daniel, thank you very much. And the floor, so to speak, is yours.
Thank you very much, Alex, for the kind words. It's very nice. Let me change my screen to my presentation, actually. Can you see my presentation now? And can you hear me, Alex? Yes, okay.
Yes, we can see and hear you. Everything is perfect. Thank you.
Okay. Let me just try to get rid of this panel here, like this. That's better. Okay, so I titled my talk, Transforming Healthcare with AI, Potential Applications and Challenges. It's, of course, a very broad topic, so I have to focus on subtopics of this to fit everything into half an hour. And that's what we are going to do. Alex was talking about unicorns just briefly. And when I started my education as a radiologist, I actually had a bit of a fear to becoming a unicorn, left out in the field, and just being in stories that are told and that are not there anymore, because one of the godfathers of AI said we should stop training radiologists now. It's just completely obvious that within 5 years, deep learning is going to do better than radiologists. That was not so nice to hear when you've just started radiology as a specialization. But he had some reason to believe that, because that was around the time when the first impressive medical publications came around. And they were published. This one was published in Nature, I think, Nature Medicine, if I'm not mistaken, and in which it was shown that AI models can actually do quite impressive things on medical images as well. So here a model was given images of skin lesions, and it was quite good at classifying those into benign or malignant lesions, and actually at a level very competitive to doctors. Although it needs to be said, of course, that doctors do much more just looking at images with a limited resolution, but they, of course, have much more information that they have to take into account, and that we'll also touch on a bit later. The hope was that AI models are going to be more accurate, less costly, of course, and have, in general, more predictive power once you use a lot of data, maybe to uncover some relations that have not been uncovered so far by humans. And the idea that Geoffrey Hinton had in mind was that by 2023, we would have a road where AI models are just zooming and humans are a bit just on the side of the road and steering the AI models into the right direction, but are not the main characters anymore. As we all know, reality is a bit different. So far, it looks a bit more like this. So there are some promising AI models, but the implementation into clinical routine is just starting within the recent years, and it's slowly progressing. It will certainly progress, but it's nowhere near the case where radiologists and medical doctors at all are not needed anymore. It's also interesting to see and look at it from the perspective of physicians to come, so medical students. And actually, those students do not worry too much that they will be replaced by AI. And what is also interesting, so here you see a graph on the left side where the students could agree or disagree entirely, disagree on the right side, agree on the left side, with these developments, that they are frightening. What you can also see is that those students who are more tech savvy, who know a bit more about the inner workings of AI models and who have a bit more of knowledge about these models, are less frightened of these models. So there's hope for all of us, I would say, and that we will still play a role, and unlike in this comic on the right side, are still in control of what we want to do. If you look at it now from the perspective of what they can do and where we are now in terms of the progression of medical AI models, the publications that I have mentioned in the beginning, this one publication in Nature, has worked with images of skin lesions at a very limited resolution. In medical imaging, there are images which have a much higher resolution, of course, and a lot of different modalities, fundoscopy and ophthalmological images, X-rays, CT and MRI images, which have a lot of three-dimensional volumes, so in terms of total pixel numbers, are much higher. And in histopathology, for example, holds light, which are examined in a very high resolution. So the total number of pixels is very, very high. So you need scalable models, of course. But we are getting there. So the models and the computational power is actually keeping step with these developments. And in our group, for example, we have also focused on some clinical problems. We have applied that to breast cancer recognition in MR images shown on the right side, and also to an automatic grading of diseases in intensive care thoracic radiographs. We did this with the idea in mind that this might be actually a useful use case for the clinical routine work, because usually these are done by radiologists, but intensive care physicians usually also look at those and sometimes even do the decision by themselves because they do not always have the possibility to wait until the radiological report is finished. What we found when we trained a model on these radiographs, and we are very fortunate in Aachen that we have a very structured database. So since 15 years, we have written our reports in a very structured way in a form where we click, there is pneumonia, there's a strong pneumonia, there's less pneumonia, etc. So we are very favored in terms of training an AI model. And when we trained that AI model, we found that this neural network model, in terms of the agreement between a test set of radiographs rated by an expert panel of 7 radiologists, was much higher. The agreement was much higher than for each individual radiologist on its own. And what is even more important, if you have a non-radiologist, that's a physician that is working in the intensive care unit, you can boost her or his performance quite considerably, even above the level of the usual radiologist. That's what we found. And that's a realistic use case that you might want to see AI models to be introduced into clinical routine. What is important is, of course, that you know why the AI model is performing this task, or why the AI model is stating that the patient is ill. And for that, there are several methods. For example, this one is a very basic method where you just state where the AI model is looking at, where you calculate these gradient cams, as they are called. That's a very rough method, but there's definitely the need for the development of more explainable methods. One field that is going to be very active, I think, in the next years to come, because that is essential to strengthen the collaboration between medical doctors and machine learning models. We have had in Germany this former chancellor of ours who said in German, wer Visionen hat, sollte zum Arzt gehen. In English, it's something like, if you have visions in terms of like maybe things that are not there, you should visit a doctor. You can take that quite literally and say, okay, if you have visions, what do you want to do with AI? You should go and visit a specialist who's specializing in AI. And I want to focus actually on 4 topics: clinical translation, which I've already touched a bit upon, multimodal data integration, which I think is going to become very important because no medical doctor is just basing his or her diagnosis just on the images or just on the laboratory data. It's always a conglomeration of all this information. And then, because we have only limited time, only quickly go through human AI interaction and very important topic of privacy and security. If you want to train large models, you need to have a way of collecting all of this data. So first of all, clinical translation. How could you do this? I think it is important when you want medical doctors to accept these AI models, that you kind of imitate the way in which a medical doctor looks at a radiograph in this case. So here we have the use case of determining a certain set of angles on a plain radiograph. It's a rather easy task, but it's a tedious task. If you have to do that multiple times a day, it's not challenging to you. It's just kind of annoying you probably because you're always doing the same thing and it's not challenging your mind. So that's in principle ideally suited for AI models to take over, at least to support this measurement. Of course, it's not helpful if you just get the angles themselves, but you want to have some kind of judging if the AI model is correct, at least in the beginning, as long as you do not trust the AI model. So what we did in order to kind of mimic the way in which radiologists approach this problem is we first trained an AI model on segmenting the bones, so that you can already check at this stage, okay, that looks right, or that doesn't look right, so I won't go to the next steps. And then using heuristic algorithms, so not any black box algorithms, but rather something which you can actually test. So for example, determining the inner point or the center of the circle of the head of the hip, we just fit a circle on this outer rim of the found segmentation. And we did so for the other points as well, and then found that in that case, we can give the radiologist an explainable approach to how the model arrives actually at those angular measurements. And that was taken up by the radiologists in our hospital quite favorably. And not only that, but we could also see that it can help to improve accuracy. So what you can see here is we had 2 radiologists rate, I think, around 100 images each. And what we see here is the mean rating of the radiologist. But more importantly, here's the difference of the measurements that the radiologist 1 and radiologist 2 had. As you can see, it's a bit, there's a large deviation between the 2 radiologists. Well, relatively large. It's 2 degrees. That's not too large, of course. So the radiologists are still fine. But if you use an AI model to do this, you can get a much more standardized approach, and you can actually see that the difference between the AI model's predictions and the predictions of the radiologists are much smaller, both for radiologist 1 and for radiologist 2, than the difference between the 2 radiologists themselves, as an indication of that the AI model might indeed be capable of performing this procedure more accurately. So this was one example of how you could approach a problem like this. And why do I think it is actually necessary to bring these things into clinical practice? I think you all know probably that the number of examinations is rising steadily all the time. And not only that, but the complexity of the examinations also rises. So when you in earlier times, you had a CT examination with maybe only 1 or 2 reconstructions. Now you have a CT examinations in which you have multiple reconstructions and multiple resolutions, maybe even some maximum intensity projections, etc., etc. So it takes more time to, at least in principle, to investigate such an examination. And what is even worse, there's the shortage of nearly every medical profession, and radiologists in particular as well. So both of these come together to establish the need for a support of radiologists in clinical practice. And of course, there is a lot of interest of commercial players in being the first ones to actually implement their model in radiological practice in this case. So it's already quite some time that I did this research here, and I searched for AI models that have been approved for use in the clinical routine. And even back then, I think it's more than a year, it was 200 AI models that you can use in principle. So there's a lot of interest both on the commercial side, but of course also on the research side. So when you now want to implement those in clinical practice, and even when you want to, when you go back a step, when you want to develop these models, you face the problem that you have a lot of data in the hospital, but this data is distributed among a lot of different systems. So in radiology, we have the PACS system, the picture archiving system. Then we have the Krankenhaus information system, the hospital information system, and the radiological information system. There's a number of fragmented information that you ideally want to combine in order to train a model. And not only these 3 examples, but we have many more in other disciplines as well. So one way to do this, of course, is just concentrating on one information content, say the images, and have an AI model then extract information from this image and put it into another image, and then you can send that image back into the PACS system. That's a way of how you could approach some problems, and that's a way of how commercial players are approaching problems where you do not need all of the information, but just the image, for example. If you want to include all of this information, you have the problems that you need an entire entity of an AI model. Say it's a separate program, and that separate program needs to have access to all of these sub-programs where all the information is stored, which is, of course, not possible to do that generally in every hospital. So an approach that is used by some of the major progressive hospitals in that case is that you build a platform which has a standardized access to all of these underlying information system. So you kind of abstract away the need to communicate with every single information system, but you have a standardized way, FHIR API, for example, or the DICOM standard, in which you can then communicate with all of this information, in which the backend apps, which are performing the actually heavy loading of the AI model analysis, then are communicating directly with these information, and where you have a front end, so the graphical user interface that we are using that can then access this apps. So that's one way of from the view of infrastructure, tackling this problem of bringing AI models into clinical routine. Now, after having touched this topic very briefly, I now want to move towards multimodal data integration, because I personally think that is going to be the future of AI models. And we see this already, like if you've seen the release of GPT-4 2 days ago or yesterday, I don't know. They are also concentrating on combining image and text embeddings so that you can do both, analyze images together with text. And in the clinics itself, we also even as radiologists, we not only look at images, but we have other image modalities as well. We have histopathology, we have nuclear medicine, and so on. But you also have a lot of laboratory values that we as radiologists also take care to take into account: genetic data, temporal changes of the images, clinical data, activity data, and so on. All of that needs to be taken into account for a proper diagnosis if you want to really diagnose complicated diseases, and not just state there's something wrong on the X-ray, but you want to really find out what is what is the base of this change? For that, there's this exciting development which has been now on like in the focus of research for quite some time, the so-called transformer architecture. Has nothing to do with this film, fortunately, but it's all about how you process the weights, how you process the inputs of that model. Most models that have been used beforehand are convolutional neural networks, which are very much suited to analyze images. Transformers are different in the way that they can also do a lot with text and that they can also be applied to images. So I fed the text, what is Zurich famous for example, to ChatGPT. All of you probably by now know ChatGPT. And it is actually quite accurate in mentioning a lot of points that are probably right about Zurich. First of all, the banking and finance sector, of course, but then also going on about arts and cultures and the scenic beauty, which is particularly nice in Zurich, I think. Let me tell you a bit about what is different between convolutional neural networks and this new transformer architecture, because I think this will help to understand why it is particularly well suited for text and why you have these new models, ChatGPT, which are so impressive in terms of generating text. So if you look at this sentence, I poured a bottle of wine into the glass until it was empty. You can ask yourself, what does it refer to? Because just from the grammatical structure, it could refer to the glass or it could refer to the bottle of wine. In this case, deducing by your understanding of the sentence, you probably know that it refers in this case to the bottle of wine, because only the bottle of wine is poured to be empty and the glass is, on the other hand, poured to become full. So if you rephrase the sentence, I poured a bottle of wine into the glass until it was full, you know that it, in this case, even though the structure is grammatically completely the same, refers to the glass instead of the bottle. That is an important task if you want to, for example, if you want, this is just repeating what I have said before, sorry, I should have clicked. If you want to translate these sentences, for example, into other languages, because in German, for example, it does make a difference if it is referring to the bottle, which has a different gender, than the glass. And so in German it would be sie or es, depending on what it is referring to. Now, if you try to frame this in the setting of neural networks and try to analyze what is said in the sentence, you could use convolutional neural networks. Convolutional neural networks work in such a way that you always look into the very vicinity of the word and you build step by step a deep neural network, which means that you have several layers in which you then process this information. In this case, the important information, the meaning of the word bottle and the meaning of the word it, is quite distant from each other. Those have not seen each other so far in this layer of the network. If you go to the next layer of the network and perform the same procedure, going through this convolutional operation, which is basically just looking at neighboring points, at neighboring words in this kind, you see that it takes quite a lot of layers. You have to go quite deep before, at the first time, the word bottle gets to know that there is a word it in the sentence, which is, of course, problematic if you want to train these kind of networks. So what you need is you need a network architecture which can actually relate these two words at an earlier level. And transformers actually do this. They have the opportunity to look at all the words and syllables within the first layer and already relate the word it to any of the words in any of the sentences. So the word it is sent to the first layer and it can kind of ask the question, what is the most important word for me to pay attention to? And then it would probably get back the feedback when the network is trained well, that empty, glass, and bottle are the most important words in this sentence for the word it. And this is then actually done mathematically in a way which I will now glance over a bit because we have only limited time, in which you actually perform this, what I said before, the word it is questioning, what is the most important word for me? And you get this information that bottle, glass, and empty are the most important words for me. And then you process this information and you do this for all of the words. And you, even at the first stage, you have in principle, at least, a complete overview over the sentence. And that is why these transformer models are much better suited to work on sentences. Now, you put this into a whole architecture. Again, I will go over this a bit more quickly. You have, again, a lot of different layers, but this time each layer is much more capable in terms of word processing because it can relate different words which are far apart. And you get these results in which you can get, for example, as well a poem about Zurich. Basically stating the same content as before that was given out by ChatGPT, but now it's in the form of a poem, which is quite nice. Actually, I used ChatGPT to send out some Christmas cards in the form of poems as a nice trick. So we saw that transformers are state-of-the-art in language processing, and we have now seen why this is the case. CNNs are state-of-the-art in image processing, so these convolutional neural networks, where you only look at the vicinity of the point that you're analyzing. But fortunately, there has been this publication, which is quite famous, in which it was proven that, or was shown at least, that transformers can also be quite capable in terms of processing of images. So they tested transformer architectures called vision transformers on images and have seen that these architectures can really perform competitive or even better as compared to CNNs. So if you instead replace the image patches against by these tokens, you see that you can perform in basically the same procedure as before with the words. I said that transformer architectures have become better than the state-of-the-art image processing. That was at least what was claimed by this paper here, an image in which they examined transformer architectures shown as circles and convolutional neural networks shown as these squares, and you can see that transformer architectures seemingly are better. Then there's another paper in which they then again show, but if you invest a bit more time into tuning CNNs, convolutional neural networks, you can again show that they are better or at least on the same level. So the question which are better is still out. I think we can state that they are both quite good in terms of image processing power, which is good for us because now we can combine these two. We can use transformers for images and we can use transformers for text. And this is text can be any information at all. It can be laboratory values, the diagnostic report written by the internal medical specialist. And this is quite handy if you want to build these kind of multimodal models. In radiology, for example, if you want to go back to a simple use case just to illustrate why this is important, you could imagine that you have bilateral masses in the CT image. So what you see here is the heart, and then you have here some masses that should not be there in principle, they are too big. And if you combine this with the laboratory value, you can actually deduce that when a laboratory value is increased, in this case ACE, that is most likely sarcoidosis instead of a malignant pathology, which is quite helpful. So this is just an example, simple example of trying to illustrate why it might be useful to combine images with text. And ultimately, of course, we want to combine images with a lot of different inputs, a lot of multimodal inputs. That's why I think that transformers can play a decisive role in making the transition to useful models in medicine, where you then put in the information that you need and you get the diagnosis from this transformer network. We have done this in a test case as well. So we've taken 3 data sets, a number of intensive care units, which were appended by laboratory values. And then we have done the same for a set from Germany. So one from the US, one from Germany. And we've also used fundoscopy images and used ophthalmology walk-ins together with associated data to prove that in the end, this is just the details of how many patients we have, so you can glance over that. If you combine that, if you put in the image data together with the non-image data, and then use that to predict the disease that the patients have, that they have a much higher area under the curve, exemplary shown here for, I think it was for this data set here, then when you use just the images without the laboratory values and all of the accompanying values, or just those values without the images. If you use both, you arrive at a much higher value of the area under the curve. So we've now had a brief glance at clinical translation, at multimodal data integration, human AI interaction, and privacy and security. I will go a bit more quickly about these topics because, as I said, due to the limited time, but it is important in order to make AI models understandable to the human mind, that you improve upon the methods that are available to actually show, in this case, the doctor, why a decision is made. We have made some work ourselves. So usually if you perform this gradient back propagation that I've shown you in the beginning, where you get these nice colorful images that in principle show where the network is looking at, if you do that, you get a quite fuzzy look of where the network is looking at. It should be looking at this part here, but it's looking at the whole image. It's certainly concentrating a bit on here, but not too much. If you do some fancy work within the networks, if you, and we have done this in this case, you can actually make this a bit more focused on the pathology at stake here. And I think this is important to make these maps not only like these fuzzy, colorful blobs, but to improve upon that. And a lot of work needs to be done there. What you can also do, and I think that's kind of illustrating why there are also chances, not only in terms of explainability, but chances in terms of discovering new ways of using these models in the clinics. If you play a bit with human AI interaction, you can train a model to predict the image appearance of radiographs. So we trained a model, and what you see here is that these radiographs continuously show a steady progression towards osteoarthritis. So this part of the bone is getting, on this part of the cartilage is getting destroyed. While it was good here, or at least better, it's slowly decreasing here, the cartilage thickness. And we trained the model just based on the first image. So the model is not seeing these images to predict the progression towards osteoarthritis. And we actually see that in many cases it is possible to do this. And when you have the images and you have a prediction, just an image-wise prediction, you can have, of course, a human rating these assumed prediction, and can have a human making the prediction: will the patient go towards osteoarthritis or not? Will he keep his cartilage? And if the doctor is given this prediction by the model as an adjunct help to do this binary diagnosis, osteoarthritis in the future, yes or no, we see that his performance, or her performance, is boosted quite considerably from when that information is not given. In terms of the AUC, you would be here, but if that information is given, you would be there. So new ways of employing these AI models in the clinics, and of opening up new ways of using medical data, are also something that we will see in the future, I think. I will glance a bit about this, go towards the next item: privacy and security. Of course, it is important to use a lot of data, in particular if you want to develop these new models like predicting the future, which are data hungry. So we used a public data set where there had been a lot of data collected by multiple sites, but if you want to apply it to new use cases, you must not only be confined to public data sets, but ideally you want to use data that is in the hospital itself. And for that, you can use federated learning, or swarm learning as we called it, with a slight twist, and where you do the updates of the model in the node itself on site. And what you do basically is you send the model around and let it learn on the local data without sharing the data, and then you send it to the next site, and then you let it learn on that site, send it to the next site, let it learn on that site. Instead of gathering all of the data and training the model centrally on all of the data, you just send the model around and the data can always stay on site. So that's a quite attractive approach. And we've also tested other approaches where you can share data in which you do not share the real data, but instead share synthetic data. So you train a model to synthetically produce X-rays, which have all of the properties of a real X-ray, but which are not a real X-ray. They are not patient related. So then you can share this these synthetic radiographs, and you can also share your data without having to face the fear of being in prison because you shared patient information. With this, I want to thank you very much for listening and giving me the opportunity to tell you a bit about what I think is going to be what are going to be the relevant progresses in the future, I think. And thank you very much in whatever language is your mother tongue.
Thank you very much to you, Daniel, for this great presentation. I liked it a lot. And yeah, now it's about question time. But before, I just wanted to remind everybody, if you need a certificate, an attendance certificate, just drop your email in the chat, and then I will collect it at the end, and we will send the certificates in the next days. Now, yeah, we're up for questions.
I have a question.
Go, Christina.
Hi. Thank you very much, Daniel. A great presentation. I'm so sorry I missed the beginning, but thank you to David. We are recording the session, so I will watch it for sure. I think it's really amazing to see how the progress is, or the technological progress is helping us to merge this information, because I think, as you said correctly, one of the main limitations is that we are developing an AI for image analysis that actually do not simulate the same way as the radiologists work, or they do not only look at the images. My question is, what is your experience about the availability of the data, the additional data you need to feed this AI model? So radiology has a great advantage of being quite structured. The other informations may be handled by other disciplines which are not so structured as radiology. Do you have some inputs there?
Great question. And that's exactly one of the main problems I think that we have to face, because not only do they have the data not structured, but also you have a lot of missing data. Sometimes you have that laboratory value for that patient, but you do not have it for the other patient, or for the other patient, you have a different laboratory value. So ultimately, you have to deal with these kind of things. Transformers are also capable of doing that. So you could, for example, when you do not have a laboratory value, just you put in an empty token. So you define a value for not having any laboratory values. And in principle, they can cope with that. And we have also trained transformer models on this kind of data, where you sometimes have the data and sometimes you don't have it. But of course, then you need a lot of data to account for. It's more complex process, right? The model needs to learn more complex reasoning, and then you again need more data. So you can deal with this. It is a challenge, and we probably need a lot of data to ultimately overcome this challenge.
I also have another question, if there is no one else. Daniel, what is your opinion? Is the work of the radiologist going to change in the future in the direction of being more a clinical subject and less a documentation subject? What's your opinion?
I think so, yes. It's always hard to make references to the future, of course, and the field is developing so rapidly, it's really amazing. But I think, and that is also my hope a bit, that these AI models can relieve us a bit from from tedious tasks as classifying, for example, mammography images into certain classes, when it's really a simple task that could be overtaken by an AI model. And then you could more concentrate on the actual clinical care and devote more time to that. I think that's a real possibility, yes.
You. Any more questions from the audience?
Yes, I have a question.
Please.
Hi, Daniel. Fantastic talk. Thank you very much. I wanted to ask your personal opinion about where you see synthetic data in the setting of applied machine learning, where you really talk about a clinical added value. What is your opinion on that?
Yes, very good question as well. In our own experiments, we found that you can train models to generate synthetic data. And when you then train a classifier model on this synthetic data only, it performs well, but a bit worse than if you had trained it on the real data. I think the question is still open of whether when you train it on a large scale, say when you train a generative model, so a model that can synthesize data on multiple sites, so on really large scale, if that can overcome that problem. And I think it can, but I think this question is still open. So there are some projects which are tackling this. And my personal opinion is that there will be a role for synthetic data, but probably not the most prominent role, maybe a niche role in which you can train then on certain subjects.
Thank you.
Yeah, I have also another question, Daniel. So actually you showed us that you have to take into account also more clinical data. It's not only images, but let's say all the large variety of different clinical informations that we have. Actually, that has been tried before. I mean, it's the IBM Watson approach, and that has failed spectacularly. So what makes you confident that now, let's say with different AI techniques, a little bit more advanced, it could be solved, that problem? Actually, because at that time, convolutional neural networks have already been available. So it's not that large change in machine learning technology, which we have seen since then.
Yes, also a very good question. I think what has convinced me a bit that this is a viable approach to pursue in the future is the progress, for example, in natural language processing. What we've seen in the past, like 2 years with these models, is that they can, based on really large data, and they use like all of the data they have available, all of the data from the internet that they can get their hands on, and probably also some data sets that they somehow got through dark channels or whatever. But when you have this large data, and when you build really large models, and the models that they are using, like only training it costs millions of dollars, then you can get models which are capable of inferring information, abstract information from limited data. And I think this can probably be transferred to the medical domain as well. So even if you only have like missing, or if you only have certain amounts of data available, in principle, this can be done, but training these kind of models will probably take a lot of resources and a lot of data gathering. But I think this is basically what is making me confident that it will work in the end, but probably not right now, but it will take some time.
Thanks. Okay, I see. So you are optimistic. So I have another question, or again, a nasty one. So you put a lot of effort in, let's say, developing transformer machine learning algorithms, but isn't that old-fashioned? I mean, today it would be, the general idea is to just collect more data. As you showed, the CNNs can do the same thing. You're just in a, let's say, a little bit more distant layer. So what you need to do is get more data and do more computation. So you get the same thing.
For images alone, that's correct. But so I showed the slide, right, where you have the competition between transformers and CNNs. And it was, in the end, the one publication said transformers are better, the other said CNNs are better. But that applies to images only. CNNs are particularly constructed to work on images, and they failed spectacularly on text. There, it's the transformer model is the undefeated winner in all categories. So it is indeed, if you want to join all of the different kinds of data, research in terms of model architecture are direly needed. I think transformer architectures are a viable candidate for future success. But maybe, who knows, in a year or so, there will be another architecture which is even more suited for multimodal data. But I think it is important to put a bit more research into that as well.
I would agree, if you just collect more data, if you have enough, also the other algorithm could do it, possibly.
Not for language, for example.
Okay, you're denying it. So you would say language processing with CNNs is not a reasonable thing to do, or what are you saying? Yeah. Okay.
Yeah.